Okay, so picking up where we left off on part 1, remember we were just talking about the kind of graph, how the temperature change graph relates to the entropy change graph of phase changes and how they're almost like opposites. So now picking up where we left off, standard molar, dang it, my bad, entropies, typo, my bad, happens, not all of us are perfect. An S naught value, this naught right here, this means at standard conditions, and standard conditions are 1 atmosphere and 298 Kelvin. And I know that that's a little confusing because you're like, wait a minute, standard temperature and pressure is 1 atmosphere and 273 Kelvin. But we're not talking about standard temperature and pressure with gases, we're talking about standard lab conditions, which is agreed upon to be 1 atmosphere and 298 Kelvin, which is about room temperature. And so the standard molar entropy of a substance is going to measure that substance's disorder. And if you're having a brain fart about what pure substances are, remember that's either an element or a compound, not mixtures. Mixtures don't fit into this. And the units on entropy, this is kind of will be a pain in your rear end. It is joules per mole Kelvin. Why they chose to go with joules when H values, and in a minute when we talk about Gibbs free energy, those values, they're all measured in kilojoules, and then all of a sudden you've got an entropy measured in joules. I think they did that just to make sure that you were paying attention. So make sure that you follow your units and you track your units through any calculations that you do, and before you do a calculation, you make sure that your units match up. So, you know, before you try to use the thermodynamic formula that I'll show you guys in a second, you got to make sure that all of your joules and your kilojoules match up. So either convert these joules to kilojoules or convert the enthalpy values into joules. I would suggest just converting everything to kilojoules because that's pretty much the accepted unit for all this thermochemistry stuff. And just a little rule of thumb, the entropy values are biggest for gases, which we just talked about, and for bigger, more complex substances. So if we were to compare propane to, say, ethane, or methane, or, you know, something small. Propane is a 3-carbon, oh wow, that's just like a really horrible drawing. I apologize for that. 3-carbon, and coming off of all of these are, you know, hydrogens. Y'all can fill those in. And say methane, which just has the 4 hydrogens and the 1 carbon. You can see this is a lot more complex looking structure than this guy. And so because of that, propane will have a higher S value than methane. So how do you calculate an entropy change? Well, conveniently, it looks exactly like the equation that we already know how to use for Hess's law, where to find the change in entropy of a reaction, you take all the entropies of the products, put them together, all the entropies of the reactants, and put them together, and then subtract products minus reactants. This funky looking backwards E or forward looking funky E thing, this means the sum of, that's all that means. So, our practice question here, what is the change in entropy, delta S, for this reaction? And I've got a couple of nitrogen monoxides reacting with some oxygen to produce 2 nitrogen dioxides. So what I want you guys to do right now is pause this, look up the standard entropy values for these 3 compounds or elements, and write them down, and then I'll show you, we'll kind of walk through this and show you what to do with them. So that's what I'm going to do. Pause it, you find it, and then hit play again. So the S value for nitrogen monoxide is 210.62. The value for oxygen is 205.0. And for nitrogen dioxide is 240.45. Now your values that you find might be just a little bit different than this, but they should be extremely close. And so if we are to calculate the change in entropy for this particular reaction, all we have to do is take the sum of the products. Well, conveniently, we only have one product. So we're going to take 2 because we got to multiply it by the coefficient that is on the chemical. So we're going to take 2 times 240.45. And now we're going to subtract the sum of the reactants. So I'm going to take 2 times the value for the nitrogen monoxide, the 210.62. And I'm going to add to that the value for the oxygen. I've only got one oxygen, so I'm just going to say 205.0. And then close that. And so this works out to be negative 145.34. And remember, the units on this are joules per mole Kelvin. And so that's how you find an entropy change. And it is exactly, mathematically speaking, exactly the same as the Hess's law equation to calculate an enthalpy change. So no difference here. You just look up the values in a table, and then plug those values into this equation right here. Alright, so that's enough for entropy for a second. Now let's talk about Gibbs free energy. I have no idea who Gibbs is, and no disrespect to Gibbs if it is really a person, but I don't really care who he is. I just know that he's the reason that this is called delta G. So Gibbs free energy is basically a measurement of the amount of energy that can be obtained from a process at constant temperature and pressure. And we've got this fantastic formula right here. You need to know this formula. So important that you know this formula. So very important. You'll notice that the formula to calculate delta G of a reaction, if you have the delta G of the products and the reactants, is exactly like Hess's law again. And again, you can look up these delta G, or these G of formation values, in a table in the back of a book. Just like the H naught values and just like the S naught values. And so, like I kind of said before, G and H are measured in kilojoules per mole, and S is in joules per mole Kelvin, so it must be converted to kilojoules. And yeah, you could convert G and H back to kilojoules, but you know what? When you got 2 in kilojoules and 1 in joules, it just makes a timely sense to convert the one that's different to what the other two are. And also because S is in joules per mole Kelvin, that means our temperature needs to always be in Kelvin as well. So what does G tell you? Well, G tells you about the spontaneity of a reaction, and that spontaneity is determined on whether or not G is positive, negative, or 0. If the change in G is negative, if G goes down, then the process is spontaneous. Now again, spontaneous doesn't mean it happens fast, just that it happens. And if the change in G, if G increases, if delta G is positive, then that means the process is not going to just happen. That means you're going to have to constantly give it a push to keep it going. And if delta G, if there is no change in G and delta G is 0, then that means the process is at equilibrium. So there is not going to be a change. There is no spontaneous forward direction, and there's no spontaneous backward reaction. And at this point, I'm actually going to go ahead and give it a break, and then come back and hopefully finish these out with one last part.